So, okay, and welcome to this another course that your power system dynamics, control and monitoring. So, before starting this course, of course, that for your little bit I would like to tell that whenever you are taking this course, you just I would like to tell that you have at least you have studied electrical machines as well as power system analysis for for undergraduate students. Those have already read machines, particularly synchronous machines, and your what you call this power system analysis, you will find things are very comfortable, right? And for postgraduate students and research scholars, they can if they want they can opt it, right? And your what you call, apart from that, in various colleges that many faculties are there, if they prefer this thing, they can also go through this lecture, right? So basically this is power system dynamics and control. It is slightly different than other courses, although you will see that your what you call that half of the portion or even more, it will be mainly your modeling and other things for synchronous machines. So apart from that, for this course we will study transient stability analysis for multi-machine system and your automatic generation control in deregulated environment, and at the same time we will see the state estimations. If time permits, I will see little bit more thing if we can add. So only thing is that this course, those who are aware of the syllabus and other thing in various colleges, right? So I will see that your what you call assignments or questions whatsoever, that it can be solved in a classroom. That way I have planned, right? And just see how is it, and mostly whatever I will show you, it is basically I have scanned my class notes, and based on that we will study that, and you will find that things are little different, but only for undergraduate students. First I would like to tell that you have covered, if you have completed electrical machines as well as power system analysis, then you are welcome and you will find things are very comfortable for you, right? And PG and research scholar also can, and teachers also, all faculties of various colleges also I will encourage, just go through this, right? So first thing is that dynamics and control, right? So first thing is that whenever we study that power system dynamics and control, the first what we will see that power system, or what you call that power system stability, right? So in that case, the definition of the stability, right? So it is something like this: the property of a power system that enables it to remain in a state of operating equilibrium under normal operating conditions, right? And to regain an acceptable state of equilibrium after being subjected to a disturbance, right? This is we define as a power system stability. That means even if it is subject to some disturbances, right, then naturally, but it will remain, it will come back to its original equilibrium point, or maybe in the vicinity of the equilibrium point. Then system should be, or what to call, a power system will be remain stable, right? So that is that property of a power system that enables it to remain in a state of operating equilibrium under normal operating conditions and to regain an acceptable state of equilibrium after being subjected to a disturbance. That means acceptable state of equilibrium means that it will be very close to its previous equilibrium point, right? And it will remain stable. So that is what you call, we define as power system stability. Okay. So just let me clear this. Now next is your power system instability, right? So another one is power system instability. Initially, first 2-3 hours lecture, this was scanned from a your what you call from photocopy. So that's why slightly faint. After that, things will be all right, right? So now question is that next is power system instability, right? So instability in a power system may be manifested in many different ways depending on the system configuration and operating mode, right? So basically in power system you will find the power generating plant, basically they are synchronous machine or synchronous generator, right? So let me clear it and let me move it up. Mathematics will come little later, right? So in power system, your since power system rely on synchronous machine for generation of electrical power, that is synchronous generator, right? A necessary condition for satisfactory system operation, right? This is satisfactory system operation is that all synchronous machines remain in synchronism, right? So they should not be fall out of step, right? So all will be remain in synchronism. This aspect of stability is influenced by the dynamics of generator rotor angles and power angle relationship, right? So this your derivation and other things later we will see. So now, so instability may also be encountered without loss of synchronism. If it is your what you call, if machine synchronous machine is fall out of step, then your what you call, there will be loss of your synchronism, right? Loss of your stability, right? So because all the machines they swing in unison, that means they are what you call, that is your they are in coherent group. That means their increase or decrease of the speed same, right? So but if one of the machine fall out of step, I will lose synchronism, then instability may happen. For example, a system consisting of synchronous generator feeding an induction motor load to a transmission line become unstable because of the collapse of load voltage, right? So that is previously you saw that loss of your what you call that synchronism. The second thing is that a system consists of suppose synchronous generator facing an just 1 minute, here N is written twice, right? Just hold on. N is written twice. Feeding an induction motor load to a transmission line becomes your unstable because of the collapse of load voltage. So this is also another kind of unstable system can occur, right? So maintenance of synchronism is not an issue in this instant, right? If you want to maintain the power system stable, that all the machines should swing in unison, they should be in synchronism, right? But in this case, synchronism is not an issue, right? So instead, the concern is the stability and control of voltage, right? This is another example of instability. So this form of instability can also occur in loads you are covering an your what you call extensive area supplied by large system, right? So in this, that means one thing is that your power system rely on synchronous generator or generation of electric power. A necessary condition of satisfactory system operation is that synchronous machine remain in synchronism, right? This aspect of stability is influenced by the dynamics of generator rotor angles and power angles relationship. If any machine falls out of step, then it will be unstable. And another example is given, that a synchronous machine feeding an induction motor load, right? And if there is a collapse of load voltage, then your what you call unstable condition may arise, right? So another thing is in the evaluation of stability, the concern is the behavior of the power system when subjected to a transient disturbance. The disturbance may be small or may be large, right? So this disturbance, it may be a small disturbance or a very large disturbance. Small disturbances in the form of your load changes take place continuously, right? And the system what you call adjusts itself to the changing conditions, right? If actually in the power system, you will find small disturbances are always there because loads are switched on off, right? This kind of disturbance is there. It is not ideally stable, right? So question is that you have to what you call some disturbance is there, but system is stable, right? So here before moving further, I will put a question, right? And you answer when you will go through this your video lecture. At that time you put the answer in the forum. The question is, suppose you are staying in the hostel, right, and you are sleeping, but you are stable, right? Or in a your what you call in your TV hall, right? There perhaps you are watching TV, some cricket match or soccer match. At that time you are also watching everything, but you are stable, right? When you are walking on the street and gossiping with your friends, you are also stable, right? When you are coming to your institute and attending the classes, you are also stable. When you are going to the library and reading books, you are also stable, right? So you are sleeping, you are stable, you are watching TV, you are stable, right? You are reading books in the library, you are stable. You are attending the classes, you are stable. And you are walking with your friends, right, and gossiping on the street, you are stable. Which one you like most, right? This is a question to you. I want a good answer among all these things, right? So anyway, so that's why you are what you call that continuously some disturbance is happening, but power system remains stable, right? So because loads are switched on and off, right? The system must be able to operate satisfactorily under these conditions and successfully supply the maximum amount of load, right? It must also capable of your what you call that your it must also it must also be capable of your surviving numerous disturbances of a severe nature, such as a short circuit on a transmission line, right? So loss of a large generator or load, or a loss of a tie between substations. Just hold on, let me clear it, let me move it, then I will tell you. So I mean, if it happens that your what you call, if large disturbance happen of a severe nature, such as short circuit on a transmission line, or loss of large generator or a load, or loss of the tie between two substations, that means actually what happened, this one that your loss of a tie, just hold on, that loss of a tie between two substations, that means I mean two substations are the loss of a tie, means that is three-phase transmission line, it is a tie line, right? If all of a sudden that power goes off, right? So all these things, so in that case that you are what you call that I mean this kind of problem will give you your what you call unstable system operation, right? So the system response to a disturbance involve much of the your what you call the equipment, because whenever any fault or any such things happen, you have your what you call so many your what components in a power system, and all will be affected because of this I mean this kind of large disturbances, right? For example, a short circuit on a critical element followed by its your isolation by protective relays will cause variations in power transfer, your what you call machine rotor speed and bus voltages. That means your what you call there will be variation in power transfer, then it will change also machine rotor speed and also the bus voltages, right? So the voltage variations will actuate both generator and transmission system voltage regulators, right? Because if fault happens, many components are there, so although relay is there to isolate the system, but all these things will be affected, right? And the speed variations will actuate your prime mover governors. Prime mover means, for example, for thermal power plant, it is turbine. Sorry, because turbine and generators, they are coupled together, right? So therefore the speed variation will actuate prime mover governors, and the change in tie line loadings may actuate your generation controls, because whenever you study that your automatic generation control in deregulated environment, we will see that two power systems are interconnected by tie lines. Tie line is a three-phase transmission line, right? So all these things will be your what you call actually be affected, right? So therefore the changes in voltage and frequency will affect loads on the system in varying degrees depending on their individual characteristics, right? So the idea is that here we are making it that the changes in voltage and frequency will affect loads on the system in varying degrees depending on their individual characteristics, because loads you will if you are aware of it, the loads you will find may be sensitive to some different type of loads are there. So many loads are sensitive to the voltage magnitude as well as the system frequency. So based on that will be also affected, right? In your, just hold on, let me go up. In addition, devices used to protect individual equipment may respond to variation in system variables and thus affect the system performance. That means if some kind of short circuit happens, many things actually will be affected, right? In any given situation, however, the responses of only a limited amount of equipment may be significant, because all all these things generally will not be considered, but a limited your what you call amount of equipment may be significant, not all, right. So therefore many assumptions are usually your what you call made to simplify the problem and to focus on your what you call factors influencing the specific type of your stability problem, right. So as a whole we need not consider as a whole all the things, but only those things will be affected more, right. So next we will come to that rotor angle stability. So this is actually it is the ability of interconnected synchronous machines of a power system to remain in synchronism, that is rotor angle stability. The stability problem involves the study of the electromechanical oscillations inherent in power system, right. So this is actually later we will see that we will study many things. First we will see slowly and slowly, it will take time, is how to develop the synchronous machine model, right, and then we will what you call we will your see that your participation factor also, because different modes are there, right. So those things also will identify, right. Some eigenvalues, eigen properties all will be required, and at the end of this course, if time permits, then I will come to the excitation system of synchronous machine, various excitation system, if time permits, right, because those excitation or exciters it will take time, right. This I have decided, if everything goes fine, if I get 2-3 hours more at the end, then only I will come to that, right? Otherwise I have to skip it, right. So the fundamental factors actually in this problem is the manner in which the power outputs of synchronous machines vary as their rotor your what you call oscillates, right. Now synchronous machine characteristics, basic characteristics associated with synchronous operation, the essential elements, the field and the armature. I told you that those who have already studied electrical machines, that you have to see that your field and the armature. Normally your what you call the field actually is on the rotor, the field is on the your rotor for and the armature is on the stator for synchronous machine, right, and field winding is excited by direct current. So how this field excited is excited by direct current, what is this mechanism? If I find time, then at the your what you call at the end of this course, if I find couple of hours time, then I will definitely try to tell you, right. Actually we read many things in the book also regarding exciter and other things, but whatever little bit I have learned from those who are really in the power station, what they have told about this your what you call that excitation of synchronous machine. If time permits, I will tell you your what you call at the end of this course, a couple of hours if I get extra, right. So when the rotor is driven by a prime mover means it is a turbine, right. When the rotor is driven by a prime mover, that is turbine and synchronous generator, they are coupled together, right. The rotating magnetic field of the field winding induces alternating voltages in the 3-phase armature windings of the stator, right, because armature is on the stator and field is on the rotor for synchronous machine, right. The frequency of the induced alternating voltages and the resulting currents that flow in the stator windings when a load is connected depends on the speed of the rotor, right. Therefore the frequency of the stator electrical quantities is the synchronized with the rotor mechanical speed, hence the name is synchronous machine, right. So question is that when the, that's why I underlined once again that when the rotor is driven by a prime mover means the turbine and generator coupled together, but let me tell you there will be no gear mechanism in between this turbine and generator, no gear, directly it is coupled, right. Your rotating magnetic field of the field winding induces alternating voltages in the 3-phase armature windings of the stator. The frequency of the induced alternating voltages and of the resulting currents that flow in the stator windings when a load is connected depends on the speed of the rotor. The frequency of the stator electrical quantities is thus synchronized with the rotor mechanical speed, right. So just hold on. right. So, hence the designation is synchronous machine, right. So, or otherwise is constant speed machine, right. So, that's why it is called your synchronous machine. Now, when two or more synchronous machines are interconnected, right, when two or just hold on, when two or more synchronous machines are interconnected, the stator voltages and currents of all the machines must have the same frequency and the rotor mechanical speed of each is synchronized to this frequency, right. Therefore, the rotors of all interconnected synchronous machines must be in synchronism, right. They are, I mean, in general they will be in coherent group, right. Their increase or decrease speed will remain same, right. So, all will be in synchronism, but all the time due to some small disturbance speed is slightly varying, it's changing very little, this way, that way, plus minus, this way it is varying, right. But they will never lose the synchronism, or they will never fall out of step, right. So, the physical arrangement, that is your, just hold on, the physical arrangement, that is the spatial distribution of the stator armature winding is such that the time varying alternating currents flowing in the three phase windings, right, your what you call, produce a rotating magnetic field that under steady state operation rotates at the same speed as the rotor, right. Therefore, the physical arrangement, that is spatial distribution of the stator armature winding is such that the time varying alternating currents flowing in the three phase winding, right, it produce a rotating magnetic field that under steady state operation rotates at the same speed as the rotor. Just hold on. The stator and rotor fields with each, just hold on, the stator and rotor field react with each other and an electromagnetic torque results from the tendency of the two fields to align themselves, right. Now, in a generator, that is in a generator, this electromagnetic torque opposes rotation of the rotor, right. So that the mechanical torque must be applied by the prime mover to sustain rotation. Prime mover means the turbine, right. Therefore, in a generator the electromagnetic torque opposes rotation of the rotor, so that the mechanical torque must be applied by the prime mover to sustain rotation. For example, that your single machine infinite bus system, right, you have studied that your transient stability analysis, just see those diagram and how things mechanical and electrical torque, some rotation, some direction is given clockwise, anti-clockwise, right, Tm minus Te, right. So, this is the idea. So, the electrical torque, right, the electrical torque I am writing in bracket in power. Later we will see that in per unit values we will see that torque and power is same. When we will neglect the your what you call that losses, we will find that torque per unit values, torque and power same. In this course we will also study per unit system for synchronous machines, that will be slightly per unit same for whether power system and this, but here slightly different you will find, right. Later we will see that, and cover that one also will take some time. So, the electrical torque, that is why I am writing in power, you assume your what you call per unit. Output of the generator is changed only by changing the mechanical torque input by the prime mover. This is single machine infinite bus, something we have studied also, right. So, the effect of increasing the mechanical torque input is to advance the rotor to a new position relative to the revolving magnetic field of the stator, right. So, now conversely, a reduction of mechanical torque, a reduction of mechanical torque or power input will retard the rotor position, I mean deceleration, right. So, under steady state operating condition, the rotor field and the revolving field of the stator have the same speed, right. So, when it is steady state operating condition, rotor field and the revolving revolving field of the stator, they have the same speed. However, there is an angular separation between them depending on the electrical torque output of the generator, right. The terms torque and power have been used interchangeably, right. So, just hold on. So, the terms torque and power have been used interchangeably, right. Now, the average rotational velocity of the machines is constant even though there may be small momentary excursions above or below synchronous speed, right. It is above or below, right, synchronous speed. The per unit values of torque and power are in fact very nearly equal. That means, because basically the loss is negligible, right. Later we will see, if loss we ignore, then you will find in per unit values power and torque will remain same. That will prove later, because this course actually have full of mathematics only, right. I mean you will later you will see that full of mathematics. That's why I told that we will set the assignment question such a fashion such that you can answer in the classroom, but it is a full of mathematics, right. Now, for example, this diagram, this is actually later after 1 or 2 hours lecture, later you will find things are okay. This is actually scanned from a photocopy, right. So, this is my generator. Suppose this is one generator, this is machine 1, right. This is my generator. I am just redrawing it for you once again. This is one, this is transmission line impedance, this is line, and this is your a motor is there, this is machine 2, a motor is there, this is a single line diagram, right. So, suppose now if you take the generator, forget about resistance, only reactance, generator reactance is Xg, line reactance is XL, right, make it this thing, right, line reactance is XL and motor reactance is Xm, right, and terminal, just let me move little bit up. Just make it further, right, this one. So, in this case your what you call, and this motor reactance is Xm, and here the voltage is ET1 and here the voltage is ET2, right, and this is your idealized model because resistance we have considered, and this is your generator voltage Eg and this is Em, motor side. Now, if you draw the phasor diagram, right. So, what we have taken? We have taken say ET2 as a reference. Suppose this is your reference, ET2 as a reference, right. This is my ET2, right. This is my ET2. Now, we are assuming that your current is flowing I. This is the current I. It is lagging current. Say current is lagging, right. This current is I, right. Now, if you say your what you call ET2 will be what? It will be Em plus Jxm. So, ET2 is equal to this is my Em. This is my Em, ET2 is equal to Em plus your Jixm. So, this angle actually 90 degree, right. So, ET2 is equal to, and this is the current, right, this is Ixm. Now, next is your ET1. If you come, just let me clear it, if you come to this diagram again, then ET1 will be Jxl plus ET2 because this is my ET1. So, current is flowing in this direction. So, ET1 will be ET2 plus Jxl. So, look at that ET1 will be ET2 plus your what you call I into Jxl, sorry, I into Jxl, right. So, here also I into Xm and here also I into your Jxl, right. And one thing is there, just one correction is there, it is actually I is actually lagging. So, your what you call this angle, your what you call, it may not be your what you call 90 degree, because I also have some angle. I previously I wrote 90 degree, it cannot be 90 degree because I also have some angle. If I angle 0, then it is 90 degree. Otherwise, if I is equal to your magnitude of I angle theta, and this is Jxm. So, basically it will be magnitude of I say into Xm, then angle your what you call 90 degree plus theta. As current is lagging, so theta will be your negative. So, in that case it will be your less than 90 degree. So, only 90 degree is possible if I your what you call your angle 0 degree, but it is not, right, it is lagging from this one. So, it cannot be 90 degree, right. I overlook that one. So, question is your what you call this one, now ET1 will be I into Jxl ET2. So, that is why ET1 is equal to ET2 into I into your JXL, right. And similarly, your next one is your then EG will be I into JXG plus ET1. Therefore, EG is equal to your ET1 plus your I into your XG, right. So, this way you have to draw, but if I is known, angle is known, XG value is known, and then we can find out the exact angle, but this is the phasor diagram, right. So, for this system, I mean step by step if you make it, then things are very simple, right. So, now delta will be the total angle, delta between your EG and your EM, right. It will be delta M plus your delta L plus delta G. So, delta G plus delta L plus delta M, this is the angle between EG and EM, this is the phasor diagram, right. And power angle characteristic, you know from your power system analysis studies or machines, this thing. So, this is my your what you call P versus delta curve, right, P angle characteristic, and therefore, the power transfer from the generator to the motor is given by P is equal to EG EM upon XT sin delta, right. This we know, we have studied already in your this thing, and XT will be sum up all the reactants, and this is equation 1. Thank you very much. We will be back again.